It is very difficult and expensive to get to space. Rockets cost many millions of dollars apiece, and often they fail miserably, losing money and lives. Right now, they are our only option for space travel, but in the future, they might not be. There are many proposed devices, each of different difficulties to build and different effectivenesses, but they all rely on building an orbital infrastructure. Throughout history, transportation has been improved by establishing infrastructure. Railroad tracks and asphalt streets are examples of this. Without infrastructure, one has to cut their own path through rough terrain, but with infrastructure, one can get from point A to point B much more easily. For space travel, one such infrastructure is known as an orbital ring. Part 1. What is an orbital ring? An orbital ring is a megastructure that would loop around a planet much like a natural ring. The key difference, however, is that it would stay in place relative to the surface of a planet, making it much more useful for surface-to-orbit travel. How would it stay in place, though? Satellites don't orbit planets at many kilometers per second just for the fun of it. To stay in orbit, an object needs enough centrifugal force to cancel out the inward force of gravity. With no or slow speeds, the centrifugal force is not enough to do so. If an orbital ring were placed on the boundary of space, 80 kilometers above the surface of the Earth, then it would quickly buckle in thousands of places and fall to the ground as the tremendous force of Earth's gravity pulls down on it. This would be the case even if the ring were made of the strongest material known to man. We need a workaround here, a way to keep a stationary ring in place while producing some upward force to combat gravity. Let's try and find it. Part 2. Back to the basics. Let's return to the idea of a natural ring system. A natural ring system is made of disconnected chunks of ice and/or rock that orbit a planet at an appropriate orbital velocity for their altitude. As ring systems can be thousands of miles tall and orbital velocities decrease with altitude, a ring system is in constant fluid motion with rocks swapping neighbors all the time. For an orbital ring, we only need a mile of height at most. If we think again of the orbital ring as a piece of infrastructure and compare 1 mile to our modern skyscrapers, we see that even that would be overkill. Regardless, when we look at rocks of roughly the same altitude in a ring system, we see that they can all move in tandem to a certain degree. Barring differences in eccentricity or inclination or gravitational disturbances from neighbors, these rocks move at the same speeds in the same directions. Hypothetically, a person could run a thin wire between all of these neighboring rocks and construct a contiguous ring. So, let's imagine that, a thin wire wrapped around the Earth, orbiting at orbital velocities. What next? Well, if we want to stay in place relative to the ground, then we need to run along the thin wire at a rate that cancels out its high speeds. Imagine a ski lift running along the length of this wire at many kilometers per second. As its speed would be dashed and no centrifugal force generated, a person inside that car would experience the full sensation of gravity. If they dropped a ball, it would fall instead of floating next to them. Hypothetically, and this is the key part, they could throw an 80-kilometer ladder off the side of this ski lift and it would stay in place on the surface of Earth. Someone could find this ladder, climb it, and get to space that easily. Now, obviously, this is a very crude demonstration of how an orbital ring could be built. This example, in and of itself, has catastrophic problems with it, but it is a proof of concept for the real deal. Think of this as a soapbox derby. And now, let's move on to a race car. Part 3. A sophisticated orbital ring. First things first, no set of ski lift wheels or any set of wheels could withstand the friction generated from running over a track at orbital velocities. That would be laughable. Instead, we need a way to have our ski lift hover over the track. Hovering is just the exchange of some force over a distance without contact, and there are a few ways to do it. One way that we make things hover is by magnetic levitation, or maglev. Maglev is the basis for those trains that move at incredibly high speeds. Using a magnetic or electromagnetic track and car, maglev allows objects to hover along a track very quickly. If we used this on our own orbital ring, we could have the track move at orbital velocities while the maglev car moves against that motion to stand still relative to the surface of Earth. Alternatively, one could use incredibly powerful lasers and the slight momentum carried by light to float above a laser array. make this into a track, and run along it to cancel out orbital velocity, and voila. One problem with this method is the immense heat that this light would carry, so a strong reflexive material would have to be chosen to keep it from burning up. With a stationary car hovering over a moving track, our orbital ring is now ready to bring things to space. So let's just throw down our ladder and no. Let's construct a better path to space. How about an 80-kilometer tall skyscraper? Unfortunately, that has problems as well. Our current tallest building is 100 times shorter than that. Even with support from the orbital ring holding it up, it would have extremely high stress values around its middle as gravity pulled down and the orbital ring pulled up. The middle 78 kilometers of the structure are liable to fall to the Earth, the top kilometer remaining as a stub that held onto the ring, and the bottom kilometer remaining as a mound of ash and rubble from the collapse. We need a way to support every piece of this building against the pull of gravity. We can't just pull on the top and hope the rest holds on. We need a force. More hovering? Sure, but this type of hovering must use slightly different forces than the ones used on the ring. Because of the shape of a tower like this, and the fact that it must be supported every step of the way, a stream of particles is needed for support rather than a rigid track. This stream of particles must be fired upwards through a vacuum inside the central support system of the tower. Every few hundred meters along the station, or more often if necessary, small machines can be added that redirect the flow of the particles from very quickly upwards to very quickly downwards. This transfers momentum and upwards force from the particles to the building meter by meter so that every piece of the building is independently supported. As the building gets higher, the particle stream thins out as more and more particles have been deflected downward. At the top, all of the particles have been redirected downward. At the base of the building, the particles that have been directed downward can be redirected upward again. If it is done correctly, the momentum can be recycled as the force of the particles transfers into the ground and the Earth, which is a safe place for it to go. Very little energy is lost in this process, and it is so effective that it can be done without an orbital ring. Freestanding towers, or space fountains many kilometers tall, could be created with this method without the use of an orbital ring. A few of these space fountains might be built before a complete orbital ring is ever constructed. Some may not even serve as a means to get to space. As the nations of the world continue to build taller and taller vanity projects, I mean skyscrapers, this method of supporting a structure might come into use. The first 5-kilometer or 10-kilometer towers will likely require this kind of support to be built. But once we get up to 80 kilometers, why do we need an orbital ring at all? We're already in space, right? While it is true that a space fountain can get you to the altitude of space, it cannot get you into orbit. If a person were to drop something off the side of an 80-kilometer tall space fountain, it would fall back to Earth because it has none of that horizontal velocity needed to maintain orbit. An orbital ring, however, aids in this cause. If your space fountain is attached to an orbital ring instead of standing alone, then you have a track moving at orbital velocity beneath your feet. All you need to do is accelerate, or decelerate depending on the reference frame, along the track, and when you are moving along it at orbital velocity, you can simply let go of it and you have achieved orbit. Part 4. A holistic view. So there we go, an orbital ring, a method of ground-to-orbit travel that only requires an elevator and a maglev train. The best part about a structure like this is that much like Rome, it won't need to be built in a day. As the race for tall skyscrapers continues, space fountains may come into fashion for relatively short buildings. As time progresses further, taller buildings will be built until a threshold is reached around 80 kilometers up, where people realize that an orbital ring can be built off of these towers. Much like a space elevator, a structure like this would greatly lower the cost of space travel. With a physical structure to climb up, one has a bridge to space. No more explosive and dangerous fuels would be required for space travel, at least not within Earth's atmosphere. Once a structure like this is built, however, how would societal systems react to it? That is an essential aspect of this conversation. However, this video has gone on long enough, so it will be a topic for another day.